So let's start with the first one. So the first example says we have 1 mole of gas. This gas is confined in a piston cylinder. Initially at 300 Kelvin, 1 megapascal, the gas is heated reversibly at constant pressure to 500 Kelvin. What are the values of Q, the values of W result from this process? Then we says the ideal heat capacity for this gas is 3R. Van der Waals parameters A and B, you have the parameters given here. So in this example, just 1 megapascal. This is equivalent to 10 bar. So here we are talking about high pressure. Here in the example, he clearly says we have real gas because he gave us information about the parameters of Van der Waals equation. So he's telling us use the real gas equation of a state, Van der Waals one, to express the characteristics of this gas. So we need to find Q, we need to find W. So this is a closed volume. So the energy balance equation, the first law of thermodynamics, the energy balance equation for this closed system can be expressed as we have delta U, change of the molar internal energy, which is U2 minus U1. This is equivalent to Q plus W of expansion contraction. So this is the equation we have here. So if we start by this one, we can start with find work of expansion contraction. So if you remember from chapter 1, we have the equation for work of expansion contraction is minus PV. Let's put it. So we have this work, or let's say it, D work is minus dPV. So we can say by integration then work of expansion contraction, this one is minus the integration from V1 to V2 P dV. Here in this problem we have constant pressure, because if you see the example, the initial pressure is 1 megapascal, the final pressure is 1 megapascal, so the pressure is constant. So this will be minus P integration from V1 to V2 dV. So this one will be minus P V2 minus V1 or P V1 minus V2. Okay. So if we return to the example we have here, so we have the value of the pressure, it's 1 megapascal. So we have this pressure here. So we need to note this, the pressure, this one is given, which is 1 megapascal. If you need to convert it to the SI system, so we need to convert megapascal to pascal. So the pressure will be 1 times 10 to the power 6 pascal. Because pascal, this is the pressure units in the SI system. But we have no idea what is the value of V1, what is the value of V2. But he said we can use Van der Waals equation of a state. So we can find V1 and V2 by using Van der Waals equation of states. So this is the equation that he mentioned in the problem we can use. So van der Waals equation of a state, we have pressure equal RT over V minus B minus A over V square. So this is the general form of van der Waals equation of a state. The value of A and the value of B was given in the problem. So oops, let me get the numbers. So we have that we have parameter A, so this one is 0.25 Pascal meter to the power 6 divided by mole square, and we have the value of the parameter B, this one is 3 times 10 to the power negative 5 meter cube per mole. So we can find V1 so initial condition, so we have initial conditions. We have pressure 1, this is 1 megapascal, and as we said, this will be 10 to the power 6 Pascal. We have temperature 1, the initial temperature is 300 Kelvin. So substitute in van der Waals equation of a state. So if you substitute in van der Waals equation of a state to find molar volume, so again you will get 3 values. Okay, the lowest one, this is for liquid, the middle one we usually neglect, and the larger value, this is for gas. Here in the example he says we have gas, and he didn't talk about anything of phase changes. So we have gas, so the largest value of molar volume, this is the value that you will have. So from van der Waals equation of a state, the molar volume, so this one will be 0.0242 meter cube per mole. And since number of moles in this example is 1 mole, then the volume will be the same as the molar volume. They will have the same value, 0.00242 meter cube. Because molar volume is volume divided by mole, so we have only 1 mole, so they will be the same. Okay? And then we will repeat the same steps to find V2. So this is V1. We will repeat the same steps to find V2. So here we need to find V2. So again, at final conditions, we have P2 is 1 megapascal. And again, megapascal, this is not SI units, so the SI units will be 10 to the power 6 Pascal. We have the final temperature, this is 500 Kelvin. So again, we will substitute in van der Waals equation of a state. And then the molar volume from van der Waals equation of a state will be 0.00413 meter cube per mole. But again, since we have 1 mole, so the final volume, V2, this will be the same as the molar volume, which is 0.00413 413 meter cube per mole. So now I have V1, I have V2. These are the values I need to have in order to find work of expansion, contraction. So substitute in work of expansion, contraction equation. And then I can find that work of expansion, contraction. So this one will be the pressure, 10 to the power 6. V1, which is 0.00242 minus V2, 0.00413. So if you substitute and use these values, then we have the work of expansion, contraction. This will be negative 1710 joule. And this is the first requirement we have. Okay. Clear? Any questions? Okay. So this will be the first part. The second part, we need to find. Let's do it here. So the second part, we need to find the delta U. So again, similar to this one, here we have an actual path. We will use the residual property to find delta U. So from using the hypothetical paths, so we can say delta U will be delta U1 plus delta U2 plus delta U3. Three paths we have, two isobaric, one isothermal. So delta U1, this is negative delta U1 residual plus delta U2 of ideal gas plus delta U3, the residual property we have here. So we have delta U1, delta U3, these are the residual property. Delta U2, this is the change in the molar internal energy if your substance is ideal gas. So always we will have two residual or two parameters will be calculated from the residual, and the one in the middle, delta U2, this one will be calculated from the ideal gas. And the first one, always note this one. Here we have delta U1 is replaced with negative delta U residual property. But delta U3, this one is replaced with positive delta U residual property. So always consider this. Delta U1 replaced with negative residual property. Delta U3 is positive residual property. Okay. So we need to find each one of them. So let's start with the first one, which is delta U of ideal gas. So we have delta U of ideal gas. Since we have CV as constant, so this one will be CV delta T. Or let's do it. Let's do it from scratch. So we have du of ideal gas. This one is CV dt. Okay. So by integration, then we have delta U of ideal gas. This one will be integration from T1 to T2 CV dt. In this problem, since CV is constant and the value of CV, this is equivalent to 3R, so this was given. So we can say delta U of ideal gas, this one will be CV integration from T1 to T2 dt So this one will be CV T2 minus T1, and we have all these values, so this will 3 times 8.314 times T2, which is 500, minus T1, which is 300, 4,988. Okay. Okay, so this one here is joule per mole. So this is the change in the molar internal energy if our substance is ideal gas. Then we still need to find the molar or residual change in molar internal energy. So in order to find delta UR, so we have here UR. Again, from the equations we have the equation to be as follows. So we have the integration from infinity to molar volume of T dP by dt at constant molar volume minus P, and all of this dV. So this is the equation that we can use to find the molar volume you have. So this term that we have here, P, T, molar volume, so this term relates the properties that we can find in equation of a state. So this term can be found from the equation of a state. So this one here can be found from equation of a state. So from van der Waals equation of a state, we can say dP over dt at constant molar volume. So this one will be R over V minus B. So this means the residual property we have, this one will be the integration of, or integration from infinity to molar volume of T times R over V minus B minus pressure. We will substitute the pressure with van der Waals equation of a state. So this one will be R T V minus P minus A over V square, and all of this dV. So again, all this term is the substitution of pressure. This is the pressure term. And we find this equation from van der Waals equation of a state. So if we did this, so what we will have this term will be cancelled with this term, and at the end I will have the residual molar internal energy. This one will be the integration from infinity to molar volume of A over V square dV. So if we did this integration, this will be minus A over V. So this one will be minus A over molar volume. And this is the residual property we have. So if you need to find the residual property for path 1, so substitute with the value of A, which is given, and the value of molar volume at the initial condition. Residual property for path 3, so we need to find the value of A, which is also given, and the molar volume at the final condition. The initial value, the initial volume, we have it already from here. We calculated it when we calculate the work of expansion contraction. So we have the value of V1. Here we have the value of V2, 0.00413. So this is everything we have. And the value of A, as we said, is given. So we can say, substitute in this equation here. So then we can say residual property 1, this one will be minus A over V1. So this one will be minus 0.25 divided by V1 0.00242. So this is the residual property number 1. Residual property number 3, this one will be minus A over V2. So this one will be minus 0.25 divided by 0.0413. So if you have all these values, so substitute in delta U equation, then we can say delta U is minus residual property number 1. So this one will be 0.25 minus minus will be plus, so this is why the minus cancelled. 0.00242 plus 4988 minus 0.25 over 0.00413. So we have all these values given. We just can substitute in this equation, and delta U, this one will be 5030 joule per mole. And this is the second requirement. So now we have delta U, we have work expansion contraction, so we can substitute in the energy balance equation. So again, energy balance equation says we have delta U, this is Q plus work of expansion contraction. So we can substitute in this one and say 5030. This is equivalent to Q plus work of expansion contraction, which is negative 1710. So from this equation, we can find Q. The amount of heat is 6740 joule per mole. And again, since we have only 1 mole, then we can say Q will be 6740 joule, and this is what we need to find.